Hello, my name is Eric Sai Cheng. My matrix number is DE2078.
Hi, my name is Ahmad Harith AKMAL. My matrix number is CE200145.
Hi, my name is Khoo Jian. My matrix number is DE200070. Now we will start to present our group project.
This project, we are required to design and simulate a 6-order bandpass active filter using an op-amp linear devices that have all the properties required for nearly ideal DC amplification and are therefore used extensively in signal conditioning, filtering, or to perform mathematical operations such as add, subtract, integration, and differentiation. The specification of the bandpass active filter using the op-amp is shown in below, which is mid-gain, A is equal to 30 amp. The low cutoff frequency is equal to 15 kilohertz, and the high cutoff frequency is 150 kHz. So as the calculation shown, the center frequency FC is equal to square root FL FH, and it is equal to 47,434.16 Hertz. So the bandwidth is FH minus FL, and we get 135K. And the quality factor, which is FC over BW, is equals to 0.3514.
To identify the parameter of each component, we have used some formulas and calculation required. For the high-pass filter, the 6th-order high-pass filter is done by connect 3 second-order high-pass filter. According to the figure, which a second-order high-pass filter circuit, there are 3 nodes which X, Y, and Z in each filter. For X nodes, AVO equal to 1 plus RF1 divided by RA1. For Y node, VI minus VY divided by 1 over SC1 plus VO minus VY divided by R1 equal to VY minus V minus divided by 1 over SC2. For the Z naught, Vy minus V negative divided by 1 over SC2 equal to V minus over R2. We assume that R1 until R6 is equal to R, while C1 until C6 is equal to C. So the AVS equal to AVO divided by 1 over SRC square plus 3 minus AVO divided by SRC plus 1. The cutoff frequency for the high-pass filter is 15K, well, which the low cutoff frequency. The formula used for the cutoff frequency is FL equal to 1 over 25 RC. We assume R equal to 10K, so the C is 1.061. After that, we use Butterworth polynomial table to find the ratio of RF over RA. As we are doing for 6-order band-pass active filter circuit, so we use the n equal to 6 in the Butterworth polynomial table. For the section 1, we assume RA1 is equal to 10K, so RF1 is equal to 14820 ohm. Section 2, we assume RA2 is equal to 10K, so RF2 is equal to 5860 ohms. For section 3, we assume RA3 is equal to 10K, so the RF3 is equal to 680 ohm. For the low-pass filter, the 6th-order low-pass filter is done by connect 3 second-order low-pass filter. According to the figure, which is a second-order low-pass filter, there are 3 nodes with X, Y, and Z in each filter. For X nodes, the AVO is equal to 1 plus RF4 over RA4. For Y node, VI minus VY over R7 plus VO minus VY divided by SC7 is equal to VY minus V negative divided by RA. For the Z node, VY minus V negative divided by RA is equal to V negative divided by 1 over SC8. We assume that R7 until R12 is equal to R, while C7 until C12 is equal to C. So the AVS is equal to AVO over 1S 1 over SRC squared plus 3 minus ABO divided by SRC plus 1. The cutoff frequency for the low pass filter is 150K, which the high cutoff frequency fh is equal to 1 over 2 pi RC. We assume that R is equal to 10K ohm, so the C is equal to 0.1061 nano F. Therefore, we can say that R7 until R12 is equal to 10K ohm, and C2 until C12 is equal to 0.1061 nano. After that, we use Butterworth polynomial table to find the ratio of RF over RA. We also choose the n equal to 6 in the Butterworth polynomial table because this is the 6th order band pass filter circuit. For section 1, we assume RA4 is equal to 10K, so RF4 is equal to 14820 ohm. Section 2, we assume RA5 is equal to 10K, so RF5 is equal to 5860 ohm. Section 3, RF6 is equal to 10K, so RF6 is equal to 680 ohm. To achieve the mid-gain, A, we use 30. A non-inverting amplifier is inserted into the circuit. The AVO is equal to 16. The AVO is equal to 17.67. VO equal to VI times 1 plus R14 divided by R13. The 1 plus R14 divided by R13 is equal to 30 divided by 17.67. The R14 is equal to 0.6978 R13. So we assume that the R13 is equal to 10K ohm. So R14 is equal to 6978 ohm.
This is the circuit of the 6th order band pass filter active circuit. The 6th order band pass filter active circuit is contributed by two different filters of the 2nd order stages. There are 3 lower pass filters which are at the bottom part cascaded together with 3 high pass filters which are at the upper part. After we run the program, we can show the graph of the 6th order band pass filter active circuit. On the graph, we can determine the low cut-off frequency, high cut-off frequency, center frequency, and the bandwidth. For the low cut-off frequency, the given value is 15 kHz, while the value that we got in the simulation is 14.3605 kHz. For high cut-off frequency, the given value is 150 kHz, while the simulated value is 120.557 kHz. For center frequency, the calculated value is 47434.616 Hz, while the simulated value is 41608.1 Hz. For bandwidth, the calculated value is 135 kHz, while the simulated value is 106.1967 kHz. This has proved that each value of the parameters between simulated value and the theory value, which are the manual calculations, will have slightly differences. Although they got some different in value, but it is acceptable because the theory value only exists in the ideal 6-band pass filter. From this project, we can conclude that the result from the construct filter doesn't have the same value as the simulated results, but it will maintain the filter behavior of characteristics. It is believed that there can be further improvement in the characteristics if more precise value of resistor and better operational amplifier were used. This filter can also be used as a narrowband device because the selectivity is high, as well as to obtain high gains.